Hello. Now let me ask you a question. Would you rather be staring into a 10-watt light bulb, or would you rather be staring into a 1 milliwatt laser beam? This is probably safer, right? The laser beam feels a lot more dangerous intuitively. But why? To answer this question, we must have the concept of intensity, which is power per unit area. Let's go back to the 10-watt light bulb. So if it's 10 watts, what does that mean? It means 10 joules of energy is leaving the light bulb per second. What happens to this 10 watts of power is propagated in all directions, right? That's what a wave does. It propagates the energy and the power. So this 10 watts, after some time, some of it will have arrived here, some of it will have arrived here, some of it will have arrived here. So if the power is distributed evenly, then this 10 watts of power would have arrived at this spherical area, which means the 10 watt power is spread evenly over this spherical surface. And the spherical surface has the formula 4 pi r squared, right? So the intensity at the distance r away would be power divided by 4 pi r squared. So for a 3D wave which propagates power in all directions, then the intensity will decrease as you go further and further away from the source. That's because the same power will have arrived at larger and larger surfaces. And since these are all spherical areas which are described by 4 pi r squared, we know that the intensity will decrease and it follows the inverse square law. The amplitude of the wave will also decrease, and since intensity is proportional to amplitude square, the amplitude will decrease following this relationship. So the amplitude is proportional to 1 over r. Now there are some waves that propagate their energy in this manner. As it propagates, it diverges only in the x and y direction. It doesn't diverge in the vertical direction. So in that case, the intensity of the wave will also decrease as you go further away. Now the areas we are looking at are actually cylindrical areas, which are described by 2 pi r, the circumference of a circle, 2 pi r, times some height here. So the intensity will decrease, but will be inversely proportional to r only, not r squared. Because it used to be spherical area, 4 pi r squared, but now it's cylindrical area, which is 2 pi r. Similarly, the amplitude will be inversely proportional to square root of the radius, because intensity is proportional to a squared, remember. Now, if the power is propagated without any divergence at all, then we have what is called a 1D wave. So in such a scenario, whatever power that leaves this area here will arrive at this area, will arrive at this area, will arrive at this area, which means the intensity is constant, regardless of the distance from the source, and therefore the amplitude is also constant. Now let's go back to our light bulb and the laser beam. So for the light bulb, we have 10 joules of energy leaving the light bulb per second, but we don't have 10 joules arriving at your eyeball per second. That's because the power is spread over a larger and larger spherical area. So the intensity of the light hitting your eyeball will depend on how far you are away from the light bulb. So suppose that this distance is 1 meter, then in that case, the intensity hitting your eye will be 10 watts divided by 4 pi 1 squared. This is a spherical area, right? 4 pi r squared. So giving you 0.8 watts per meter square. As for the laser, the intensity doesn't decrease with distance, because it doesn't diverge. So whatever intensity here is the intensity here. So let's calculate the intensity at the point where it leaves the laser pointer. So we have to estimate this area, the cross-sectional area of the laser beam. I'm going to go with 5 millimeter square. That sounds reasonable, So you have 1 milliwatts divided by 5 millimeter square. And turns out the intensity is 40 watts per meter square, much higher than what the light bulb hits you with. So our intuition was right that the laser beam is probably more dangerous, but now you know the reason why. Alright, that's all. Ta-ta!